This is a capacitor bank single line diagram, a whole power factor correction bank, drawn as one clean line from the incoming bus down to the switch capacitor steps. If you have ever been hit with a low power factor penalty on a utility bill or sized a PFC-bank for a plant, this is the drawing at the center of it. One page, the whole bank, the controller, every step, and the protection around each one. So let us rewind it and build this capacitor bank single line diagram up block by block, bus, breaker, controller, and the steps so that by the end you can read one at a glance and draw your own. First, why this bank exists at all. Motors, transformers, and fluorescent gear all draw reactive power, current that does no useful work but still flows in your cables and still shows up on your bill. A power factor correction capacitor bank fixes that. It supplies that reactive power right at the load, locally, so the utility does not have to push it down the line. And it earns its place three ways. It corrects your power factor up toward unity. It kills the low power factor surcharge and often the demand charge on your bill. And it frees up capacity. Less reactive current means cooler cables and spare kilovolt amps you can actually use. That is the promise of the capacitor bank single line diagram. Reactive power supplied at the load on one readable page. So let us follow the power. Here is the whole chain, the way this drawing reads. Top down into the bus, then the steps hanging off it. The feed comes in from a supply, three-phase, at your panel voltage. It runs through a main breaker or a fuse switch for short circuit protection. That lands on a bus, the bar the whole bank hangs from. Watching that bus is the PFC controller, the brain measuring the power factor. And dropping off the bus are the capacitor steps, each one a switchable block of correction. Learn that shape, bus, breaker, controller, steps, and the whole diagram opens up. Let's take it one block at a time. Quick note before we do. Every symbol in this video lives in a free editor that runs right in your browser, CircuitDiagramMaker.app. No install, no sign up. Open it in a second tab, and you could drop these same blocks in as we go. The link is below. Block 1, the incoming supply, the main breaker, and the bus. On the left, the feeder comes in, your three-phase supply at the panel voltage. Right after it comes the main protection, a circuit breaker or a fuse switch sitting across the line. Its job is short circuit protection for the whole bank. If a fault dumps huge current, this is what clears it, and its rating goes right on the page. From there, the line lands on the PFC bus, the bar every capacitor step taps off in parallel. Supply, breaker, bus. That is where the bank begins. Block 2 and the brain of the whole thing, the power factor correction controller. The controller sits off to the side and watches the incoming line, usually through a current transformer, a CT, clamped on the feeder. From the current and the voltage, it computes the real power factor, the cosine phi, right now. Then it does the one job the whole bank exists for. It switches capacitor steps in and out to hit a target power factor, typically around 0.95. If the plant draws more reactive power, it brings more steps in. If the load falls, it drops steps out so you never overcorrect and swing the other way. The controller is what makes this an automatic bank, not a fixed one. Block 3, in the heart of the bank, a single step, and every step is built the same way. At the top of the step is a contactor, the coil-driven switch the controller closes to bring that block of capacitance online. You will spot it by the little arc on the moving contact, just like a motor contactor. But there's a catch with capacitors. The instant you connect one, it pulls a huge inrush current, far more than its steady current. So directly below the contactor sits an inrush current limiter, a small pre-charge reactor, an inductor, or sometimes a resistor, that tames that switch-on surge so it does not weld the contacts or trip the breaker. Contactor, then reactor. The same pattern repeats on every step. Block 4. The step fuses and the capacitor units themselves. Under the reactor, each phase of the step gets a fuse. If a single capacitor fails, and capacitors do fail short, the fuse clears that one fast, so one bad cap cannot take down the whole bank or feed a fault. And below the fuses, the capacitors. On the single line diagram, they're the classic symbol, the parallel plate marks, 3 of them for a 3-phase step. These are the kilovolt amps reactive, the kVAr, that actually correct the power factor. Each step is rated in kVAr, and the controller sums the steps it has switched in to reach your target. Fuses to protect them, capacitors to do the work. Block 5, and the one people forget, the discharge resistor across every step. A capacitor does not empty itself when you switch it off. It holds its charge, sitting there at full voltage, sometimes for minutes. That is dangerous for anyone servicing the panel, and it also means you cannot safely reclose the step until it has bled down. So across each capacitor step, you draw a discharge resistor. Its only job is to slowly bleed that stored charge away after the step opens, pulling the voltage down below a safe level, typically 50 volts, before the contactor is allowed to close again. It protects the people who service the bank, and it protects the caps from being switched onto a residual charge. Draw the discharge resistor every step. Now, one more device the one line has to tell you about, where harmonics live, the detuning or harmonic reactor. In a plant full of variable speed drives and rectifiers, the supply is full of harmonic currents. And a bare capacitor bank is dangerous around harmonics. It can resonate with the system, amplify those currents, and blow the caps. The fix is a reactor in series with each step. The same inductor position we use for inrush, but now sized deliberately to detune the step. It shifts the resonant point of that capacitor plus reactor branch below the lowest troublesome harmonic, commonly around the 5th, so the bank can never resonate on it. Where there are harmonics, that series reactor is not optional. On the one line, you show it in series, above the capacitors on every step. So watch the bank actually run. This is what makes an automatic bank different from a fixed one. At light load, the power factor is poor, say 0.78, and the controller has only a step or 2 in. As the plant loads up and draws more reactive power, the controller closes more step contactors, bringing more kVAr online, and the measured power factor climbs toward the target. Then the shift ends, the load falls away, and the controller drops steps back out, so the bank never overcorrects in a leading power factor. Steps in as reactive demand rises, steps out as it falls. That constant balancing act, holding the line at the target, is the controller's whole day. Step back and look at the protection, because a capacitor bank has layers of it, and the one line shows everyone. At the top, the main breaker or fuse switch clears a bank-wide fault. On each step, the fuses clear a single failed capacitor. Across each step, the discharge resistor makes the caps safe to touch and safe to reswitch. In series with each step, the detuning reactor keeps harmonics from destroying the caps. The controller itself protects against overcorrection and overvoltage, dropping steps out when it must. And running underneath all of it, earthing and bonding. The bank enclosure, the frames, every metal part tied together and down to earth. On the single line diagram that shows up as an earth line reaching every step. Draw the earth every time. So step back and look at what you have. Standard symbols in a standard order. A supply source for the bus. A switch with a cross for the breaker. A little box, cosφ, for the PFC controller. A switch with an arc for each step contactor. A coil for the reactor. A fuse for each step. The parallel plate marks for the capacitors. A resistor for the discharge. And earth reaching all of it. That is the whole language of a capacitor bank single line diagram. And it is exactly why the drawing exists, because anyone who knows these symbols can pick up your page and read the entire bank without ever opening the panel. That is what the panel builder works from. That is what the inspector checks. And that is what protects the people who service it later. Let's recap the line. The incoming bus and supply. A main breaker or fuse switch with its rating. The PFC controller measuring power factor and switching the steps. Then each step, a contactor, an inrush reactor, the step fuses, and the capacitor units. A discharge resistor across every step. A detuning reactor in series where harmonics live. And earth bonding all of it together. If you want the ground level basics of single line diagrams first, what one line and 3 phases really mean, Watch our single